Hi everyone, welcome to Algebra 1. I hope you're all in good health and doing well. So today we're going to discuss permutations, and in this video I'm going to walk you through a set of slides. There will be some exercise as well. So grab pen and paper and let's get started. Let x be a set. S of x consists of all bijections from x to itself. With the usual composition of functions, this becomes a group. Today we'll focus on the case that x is a finite set. Usually we take x to be the elements 1, 2, 3 and so on up to n. In this case we use the shorthand notation Sn, which is the symmetric group on n elements. The elements of Sn are called permutations. Let's consider the following two permutations sigma and tau in the group S4. When writing down permutations, we use the following notation. The top row are just the elements 1, 2, 3 and so on up to n, and the bottom row consists of the images sigma 1, sigma 2 and so on up to sigma n. When composing two permutations, remember that we are composing functions. So the permutation sigma tau means that we first apply tau and then sigma. So sigma tau of 1 is sigma of tau of 1. In this case, that is sigma of 2, which is 4. Taking sigma and tau from the example and computing sigma tau and tau sigma, we get the following results, which we've written in our compact notation. It's clear that in the example sigma and tau do not commute. In general, Sn is not abelian when n is at least 3. Note that our notation for permutations makes it really easy to compute the inverse. Just swap the bottom and the top row and then rearrange the columns so that the top elements are again in the correct order 1, 2 and so on up to n. That will give you the inverse permutation. Now that we've seen the basic definitions, let's try some quick questions. Try the following three exercises. The first one should be easy. Exercise 2 and 3 might be a little bit tougher. Let's consider the permutation sigma. It turns out to be very useful to draw sigma in the form of a diagram, as we've done here. For every element from 1 to 8, we've drawn an arrow from an element to its image under the permutation sigma. So 1 goes to 4, 4 goes to 7, 7 goes back to 1. And the same for the elements 2, 8, 5, 3 and 6. Instead of drawing diagrams, we can also use the following notation. For each cycle, we write down the elements in the order in which they occur along the cycle. So 1, 4, 7 for the first cycle, and 2, 8, 5, 3, 6 for the second cycle. This way we have written sigma as a product of disjoint cycles. We'll come back to this notation later on. Using the diagram that we drew for sigma, it's now easy to solve the problems. In the first problem, we were interested in sigma squared. That means we apply sigma 2 times. So to find the image of element 1, say, we just have to go 2 arrows along the cycle. So from 1 we go to 4 and then to 7. From 2 we go to 8 and then to 5. This way we obtain sigma squared. In the second problem, we're considering powers of sigma. We are interested in those powers of sigma for which all elements are fixed. Or in other words, we're looking for those k for which sigma to the power k is the identity. Looking at the first cycle, we see that those elements are fixed if and only if k is a multiple of 3. In the second cycle, Every element is fixed if and only if k is a multiple of 5. So we can conclude that sigma to the power k is the identity if and only if k is a multiple of 15. From the diagram, it is now also completely clear that there's no power of sigma for which sigma to the power k of 2 is equal to 7. That's because 2 and 7 are in two different cycles. Let's describe cyclic permutations and the decomposition into cycles a little bit more formally. Suppose that we have k distinct elements, a1, a2 up to ak, from the set from 1 to n. And suppose that we have a permutation sigma with the property that it maps a1 to a2, a2 to a3 and so on, and it maps ak back to a1. Furthermore, suppose that sigma leaves all the other elements from 1 to n fixed. In this case, we call sigma a cycle of length k, and to denote it, we write the elements 1 to k between brackets. In the diagram on the right, you see a picture of this cyclic permutation sigma, just as we've seen before. The smallest possible length of a cycle is length k is 1. This is, however, not a very interesting permutation because it leaves all the elements fixed. It's just the identity element. More interesting are the cycles of length 2. These have a special name, they're called transpositions. In the example you see two permutations. The one on the top is a cycle of length 3. The one on the bottom is a transposition, a cycle of length 2. Note that there is more than one way to write down the same cycle. The cycle 1, 3, 4 is the same as the cycle 3, 4, 1 is the same as the cycle 4, 1, 3. This is not the same as the opposite cycle 1, 4, 3. Two cycles are called disjoint if they don't have any element in common. In the example you see permutation of the elements 1 to 10. The permutation is written as the product of three disjoint cycles. Since disjoint cycles commute, we could also change the order of the three cycles and get the same permutation. Also, we could include cycles of length 1. The following theorem shows that every permutation can be written as the product of disjoint cycles. Moreover, this can be done in essentially only one way. It is unique up to changing the orders of the cycles because they commute, and possibly including cycles of length 1. Let's try the following two quick questions. In question 2, be careful that you compose the two permutations in the right order. Here are the solutions to exercises 1 and 2. Note that in exercise 1 you can include cycles of length 1 or you can leave them out. In exercise 2 we compose two cyclic permutations. Take care to compose them in the correct order. Indeed, in this case the two cycles are not disjoint and the outcome depends on the order in which we compose them. A different way of decomposing permutations is as a product of transpositions. The following theorem says that any permutation can be written as a product of transpositions. These transpositions do not have to be disjoint. Let's look at the proof. We start with the simple case that sigma is a cyclic permutation of length k. Let's say it's a permutation that sends a1 to a2 and so on up to ak and ak back to a1. We can write this as the product of k transpositions as shown here. A small example where the 5-cycle 31459 is decomposed into 5 transpositions is shown here. If you want, you can pause the video now and verify all the steps. Now that we've shown that any cyclic permutation is the product of transpositions, the theorem follows from the fact that any permutation is the product of cyclic permutations. Indeed, writing each of these cyclic permutations as a product of transpositions, we obtain a decomposition of our original permutation as a product of transpositions. This completes the proof. Note that the transpositions in the theorem are not necessarily disjoint. Also, there can be more than one way of decomposing a given permutation into transpositions, even if we require that the number of transpositions, is minimal. Let sigma be a permutation. A pair of elements I, j is called an inversion if I is smaller than j, but sigma I is bigger than sigma j. Let's consider the permutation sigma in the example. We find all the inversions by checking for every pair ij with I smaller than j whether it's an inversion. For example, the pair 1, 4 is an inversion because sigma 1, which is 3, is bigger than sigma 4, which is 2. There's also a more graphical way to count the number of inversions of a permutation. In the top row we write elements from 1 to n, and also in the bottom row we write elements from 1 to n. Now we connect any element from the top row to each image under sigma in the bottom row. This gives us a graphical representation of the permutation sigma. Next, we count the number of intersections of lines in the diagram. This will give us the number of inversions. Given a permutation sigma, we say that sigma is an even permutation if the number of inversions is even. If the number of inversions is odd, we say that sigma is an odd permutation. This is called the parity of the permutation. The sign of the permutation is -1 to the power of the number of inversions. So an even permutation has 1 as sign, and an odd permutation has -1 as sign. The permutation sigma from the example had 5 inversions. So this sigma is an odd permutation, and its sign, epsilon of sigma, is equal to -1. Every permutation has a sign which is an element from -1, 1. This gives us a map epsilon from Sn to ±1 that assigns to any permutation its sign. The next theorem says that this map epsilon is in fact a group homomorphism. Let's see how the proof works. We start by taking arbitrary sigma and tau from Sn. What we need to prove is that epsilon of sigma tau is equal to epsilon sigma times epsilon tau. The key of the proof is to count inversions in a very clever way. We start by taking the set of all pairs I and j with I smaller than j and partitioning this into 4 sets A, B, C and D. To do this, consider a pair ij with I smaller than j. If the pair is not an inversion for tau and also not an inversion for sigma tau, then we put a pair in A. If the pair is not an inversion for tau, but it is an inversion for sigma tau, then we put a pair in B. If the pair is an inversion for tau, but not for sigma tau, then we put it in D. Finally, if the pair is an inversion for tau and also for sigma tau, then we put it in C. In the diagram, you see a more graphical way to represent the sets A, B, C, and D. Check that this matches the definition given above. It is now easy to check that the inversions for tau are precisely the pairs ij that are in C or in D. This means that epsilon of tau is equal to minus 1 to the power the number of elements of C plus the number of elements in D. In the same way, the inversions of sigma tau are precisely those pairs ij that belong to B or C. This means that epsilon of sigma tau is minus 1 to the power B plus C. The big question, of course, is how do we compute the number of inversions for sigma? Let's compute the number of inversions of sigma. Instead of counting the pairs ij such that ij is an inversion of sigma, we count the pairs tau I, tau j that are an inversion of sigma. Since tau is a bijection, these are exactly the same pairs. If we consider the pairs tau I, tau j that are an inversion of sigma, then there are two possibilities. Either I is smaller than j or I is bigger than j. The pairs of the first form, that is, I is smaller than j and tau I, tau j is an inversion of sigma, are precisely the pairs that are in the set B. The pairs of the other type, that is, I is bigger than j and tau I, tau j an inversion of sigma, exactly correspond to the elements of D if we swap the elements I and j. So now we can conclude that the number of inversions of sigma is equal to the number of elements in B plus the number of elements in D. That is, the sign of sigma, epsilon sigma, is equal to minus 1 to the number of elements of B plus the number of elements in D. A small calculation now shows that epsilon sigma times epsilon tau is equal to epsilon of sigma tau, and this concludes the proof. Let's start by computing the sign of the simplest type of permutations, namely transpositions. Let's consider a transposition sigma in Sn that transposes the elements A and B, with A smaller than B, and let's count the number of inversions. Of course, the pair AB itself is an inversion, but it's not the only one. For every element between A and B, there are two additional inversions. We conclude that a transposition is an odd permutation and its sign is equal to minus 1. Using the fact that the sign map epsilon is a group homomorphism, we can now easily compute the sign of any permutation. This is the content of the following theorem. As we've seen, a transposition always has sign minus 1. We have seen that the cycle of length k can always be written as a product of k minus 1 transpositions. And since epsilon is a group homomorphism, epsilon of a k cycle is equal to minus 1 to the power k minus 1. A quick word of caution, so this means that an even length cycle is an odd permutation, and conversely an odd length cycle is an even permutation. If our permutation sigma is the product of multiple cycles, say cycles of lengths k1, k2 up to km, then the sign epsilon sigma is equal to the products of the signs of the cycles, which amounts to minus 1 to the power k1 plus k2 and so on plus km minus m. In the next question, see if you can determine the sign of the given permutations. Use the fact that epsilon is a homomorphism. One way to compute the sign of sigma is to count the number of inversions. However, this is quite a tedious work and very prone to error, which makes nobody happy. A much easier way is to first decompose sigma as the product of disjoint cycles. Then we determine the sign of each of the cycles separately and use the fact that epsilon is a homomorphism. To compute the sign of a power of sigma, we again use the fact that epsilon is a group homomorphism. Note that the sign of sigma inverse is the inverse of the sign of sigma. Consider again the sign map epsilon. Since this is a homomorphism, it's natural to look at the kernel of epsilon. The kernel consists of all the permutations that are even, and, since it's the kernel of a homomorphism, it is a subgroup of Sn. This subgroup is called An, the alternating group. If we fix a transposition, say the transposition 1, 2, then multiplication by this transposition gives a bijection between the even permutations and odd permutations. So we see that An contains exactly half of all the elements of Sn. So An has n factorial divided by 2 elements. We've seen before that any permutation can be written as the product of cycles of length 2 of transpositions. If sigma is an even permutation, we can say something stronger. In that case, sigma is the product of cycles of length 3. In the example, you see how a 5 cycle can be written as the product of 2 3 cycles. Let's take a look at the proof. We already know that sigma can be written as the product of transpositions. Since every transposition is odd and sigma is an even permutation, this means that sigma is the product of an even number of transpositions. To prove the theorem, it suffices to show that the product of 2 transpositions can be written as the product of cycles of length 3. There are 3 cases to consider. The first case is when the 2 transpositions are the same. The second case is when the 2 transpositions share one common element. And the third case is when the 2 transpositions are disjoint. The first case is easy. The product of 2 equal transpositions is the identity element. And the identity element is the product of 0 cycles of length 3. It is the empty product. In the second case, the product of the 2 transpositions is a cycle of length 3 and we're done as well. The last case, the product of 2 disjoint transpositions, turns out to be the product of 2 cycles of length 3. This completes the proof. The last theorem of this lecture will be Cayley's theorem. In the past lectures we've already seen many different groups, in particular many finite groups, for example the Klein 4 group, the quaternion group, the integers modulo n, the dihedral groups, and so on. Many more finite groups exist. However, Cayley's theorem says that every finite group is a subgroup of some symmetric group Sn. The idea of the proof is the following. Consider any element A in the group G. This will give us a bijection from G to G via left multiplication by the element A. So we map any element x to Ax, and this is a bijection from G to G. Let's denote the left multiplication by A by the map lambda A. So what we get is a map from G to S of G that sends any element A to lambda A. This map is a homomorphism because multiplying from the left by AB is the same as first multiplying from the left by B and then multiplying from the left by A. So lambda AB is the same as lambda A composed with lambda B. So we have a group homomorphism F from G to SG. Let's look at the kernel of this map. An element A is in the kernel of F if the image lambda A is the identity map. However, multiplication by A can only be the identity if A is the identity element itself. It follows that the kernel of F only consists of the identity element. That is, F is an injective map. It follows that G is isomorphic to the image of G under F. So G is isomorphic to a subgroup of SG. To digest Cayley's theorem, let's look at an example. As group, we take the Klein 4 group. Let's consider an element of V4. Let's take the element A. And let's consider the left multiplication by A lambda A. Lambda A maps the identity element to A. It maps A to A squared, which is the identity element. It maps B to AB, which is C. And it maps C to AC, which is B. So lambda A gives a permutation of the elements E, A, B, C. And if you write it in disjoint cycle notation, we get two cycles, the cycle EA and the cycle BC. We can do the same thing for the other elements E, B, and C. Thus, we found a permutation for each of the elements of the Klein 4 group. If we number the elements of the Klein 4 group 1, 2, 3, 4, then we find a subgroup of S4 that's isomorphic to the Klein 4 group. To see if you fully understood Cayley's construction, try it yourself in the next exercise. Show that the dihedral group D3 is isomorphic to a subgroup of the symmetric group on 6 elements. Here you can see how Cayley's construction works for the dihedral group D3. We obtain a subgroup H of S6 that is isomorphic to D3. The second exercise shows that the number 6 is not optimal. D3 is not only isomorphic to a subgroup of S6, it is also isomorphic to a subgroup of S3. In fact, it is equal to S3. An explicit isomorphism from D3 to S3 is given here. If you're up for a challenge, you could try Cayley's construction with the quaternion group. The quaternion group Q is isomorphic to a subgroup of S8. However, in this case, the 8 is optimal. Q is not a subgroup of Sn for any n smaller than 8. Good luck! Alright, we've come to the end of this lecture. Please try to do all the exercises listed on Brightspace. If you have any questions about the exercises or the material, don't hesitate to go to the forum and post your question online. That's it for now. Take care and see you next time.